is chapter 20 and 21. There may be a little bit of familiarity within this because the first part of 20 and 21 are all doing nucleophilic additions. And the newest part is the nucleophilic or the nucleophile elimination. Okay. We saw this mechanism already when we did the enamine, or sorry, the imine formation, and that's just happened to be the examples that I chose from here. When we're talking about the nucleophilic addition and elimination, we're very typically talking about carboxylic acid derivatives. Right? Notice neither of the starting materials we're looking at in the mechanism pieces shown here are carboxylic acid derivatives. Right? But it's the acid derivative that's really kind of the centerpiece within this mechanism. We get bits and pieces of it showing up in other cases. Right? So, in your nucleophilic addition, what happens? So as a hint, the nucleophilic addition would be this first one. This is a nucleophilic addition. What happened? Say that again, Wyatt? Okay. Notice that we lose the pi bond, or loss of a pi bond. Okay. Anything involving pi bonds, we should be a little bit careful in referencing the loss thereof, because arguably, I mean, we could just go through and show a resonance structure where we don't have that pi bond anymore. Okay, so it becomes a little bit weird to refer to it as that. But what we're looking at is for sure, ultimately, the pi bond has disappeared from our system. Okay. By doing what? Okay. Gain of a sigma bond. Okay. Officially, in a nucleophilic addition, it's a gain of 2 sigma bonds. Okay. One of those sigma bonds, in this particular case, is going to a nucleophile. Okay. The other one is usually to a hydrogen. Okay. And it's just a question of how that reaction occurs. Okay. So this mechanistic step is just the nucleophilic addition. Okay. We've added to the pi bond. Our oxygen already gained that hydrogen, and so this one fits in kind of a weird category for a nucleophilic addition. We are adding a nucleophile to the pi bond, but the addition of the hydrogen technically already happened. Okay. The other one. What the heck is a nomencalture? Because some people don't see it. It's the nucleophilic addition, but backwards because what are we doing? It's going backwards. We're reforming the pi bond. Okay? In the process of reforming that pi bond, what happens? So we are now doing an elimination because we formed a pi bond. What had to happen? A leaving group has to leave. That leaving group is a nucleophile. So what we're looking at is a nucleophilic elimination. Okay. Slightly different variation from the eliminations that we've seen before, which were technically electrophile eliminations. Okay. So it's now a question of how do we stack these two mechanisms with each other, and in particular, centered on the carboxylic acid derivative, okay, which we have kind of looked at. If we erase some of that and look at a carboxylic acid derivative, let's just look at a carboxylic acid. Why not? The nucleophilic addition we've added the nucleophile to our structure. Is that structure stable? No, because it's charged, so what can we do? We get rid of that charge by having the negative come crashing back down, and kick out a leaving group. The result is that we've reformed the pi bond, except it sure looks like we've done a substitution, okay, where we've substituted the OH for Cl in this case. Everybody see that? Okay. Would I predict that reaction to be functional? As in, should that reaction actually occur? Why not? OH is a bad leaving group. Okay? So the nucleophilic elimination, or nucleophile elimination, is bad because we have OH as a leaving group. It's bad because chloride is more stable than hydroxide, meaning what? Chloride would be more likely to leave, meaning it should never have attacked from the beginning, from the outset. Okay? So this is a horrible example for a nucleophilic addition elimination because it didn't work. Okay? So there's rules behind why and when different reactions work, and that's part of what this next unit is talking about. Looking at those conditions and how can we interconvert between our different acid derivatives. We started with an acid in this case, literally a carboxylic acid, and we end with, in this case, it's an acyl chloride. That is an acid derivative because I started with an acid and I derivated it to the acyl chloride. Okay? So when we're looking at the structures involved in our nucleophilic addition eliminations, they're all centered on some form of our acid derivatives. Okay? We're following the same mechanistic understanding that we've seen in the previous sections, which means there really is no new material for me to discuss. So let's just go ahead and do a quiz, and you can prove that. So for those people coming in and now seeing all these answers drawn up, I do not vouch for any of these answers. I'm not saying they're wrong. I'm just saying I don't vouch for any of them yet. Okay, so where do you guys want to start? 1. Okay. So yeah, it didn't hurt. Let's go ahead and start with 1. So what we could go through and do is follow the pattern that I just started the lecture with, saying, oh, we're going to talk about nucleophilic addition elimination, which means we should take our nucleophile, or find our nucleophile. Well, we have an ionic bond between the sodium and the oxygen. So we have a negative, and then we have the sodium positive, right? So we have a nucleophile in that oxygen. It could go through, do the nucleophilic addition, which forms a rough equivalent of a hydrate. And as we learned in the previous section, the hydrate is unstable, and it will revert back down to kick out a leaving group. That leaving group would either be the red oxygen I just put in or the OH. What do you think? That was a question for you. Which is the better leaving group? They're both pretty much the same. So let's just pick the one we want. Let's just kick out the OH. Okay? So I agree with what was drawn up as an intermediate, as a potential intermediate. But because of that negative charge, that is now bad, and all we are looking at here is what is known as the tetrahedral intermediate. Those of you in lab don't have an excuse because you just talked about it. We had a quiz about the tetrahedral intermediate. Okay, the tetrahedral intermediate, because our carbon there is sp3 hybridized, making it tetrahedral. So the carbon where the chemistry occurred started sp2, went to sp3, trigonal planar to tetrahedral. That's a tetrahedral intermediate. Okay? That is higher in energy because it is charged. Okay? Nearly all mechanistic steps, we almost always go up in energy. Okay? Not always the case, but pretty standard. Okay? That structure would then fall apart. The electrons come back down, and that's where we kick out a leaving group. Okay? You guys said we should kick out hydroxide. So a slightly better product would then be this character with OH minus as our leaving group left over, right? Now we've done the nucleophilic and the nucleophilic addition and the nucleophile elimination. Mike should be happy, but he's not. What did I kick out? A bad leaving group. Why is it a bad leaving group? It's charged. Okay, so charge is usually a bad thing. We can kick out leaving groups if they're large, okay, or have some stabilization. Oxygen isn't large enough or stable enough. Okay. The other characteristic, if we remember all the way back to first semester, that typically leaving groups get labeled is that they're poor bases, okay, or they're weak bases. Well, what can you tell me about hydroxide? That's a strong base. Okay, well, what can you tell me about the ethoxide? So the ethoxide is our starting material, this guy. We have 2 carbons and then the oxygen. So ethoxide, that is strong base. Also a strong base. So I'm running this reaction under basic conditions. Okay, which means under no circumstances should I see acids. What functional group do I start with?
Carboxylic acid.
Carboxylic acid. So the very first thing I need to do, and I like where you went with this, you tried to neutralize that negative oxygen. We have to neutralize it with the most positive thing. The most positive thing is the hydrogen on that structure. We know it to be acidic because it's a carboxylic acid. What's going to happen is, unfortunately, none of the nucleophilic addition and elimination, and all of those arrows become ultimately invalid, and all that really happens is the acid-base step where I go through and form this guy, which is a carboxylate. Okay? So focus on your charges, and it's going to be important to be thinking about them, but we also have to realize that we can neutralize bases or strong nucleophiles with acids. We have to watch out for that. Okay? Kind of makes sense? So that would be an acceptable answer for question number 1, or no reaction. Because more than likely what's happening is we're following this up with an acid workup and we end up right back where we started. Okay? So both of those answers would work. We're just going to follow through the line?
Yeah, sure.
Okay. Purple, number 2. Okay. So we've got the nitrogen acting as what? Okay, a nucleophile. What does that mean it needs to react with? An electrophile. So you had that nucleophilic nitrogen attack this carbon because it was electrophilic. Why is it electrophilic? And remember, this totally high pressure, right? Like there isn't judgment here. We just need to be looking at these structures and thinking about them. Okay? So why did you say that was electrophilic? I don't know. Was that you? Okay. Don't know?
I was just thinking because it wasn't a super strong one that it would have attacked the...
Okay. And the group over here had the same kind of argument. Okay. So this, admittedly, is probably going to be a horrible reaction to run because there's multiple possibilities that can come out of this. So what you are thinking of is that this is not a stupid nuke, which then means it would attack a weaker electrophilic site. Okay. If we say had an alpha-beta unsaturated carbonyl, right? Alpha, beta, okay? Which is decent thought, okay? But let's push it a little bit further, okay? Why would that introduce another electrophilic site? Well, the oxygen is still electronegative, withdrawing the electrons, making this carbon partially positive. Okay? But you said not a direct attack because of that unsaturation. Fair enough. So let's see what happens if we do resonance to stabilize that positive. That then means what atom is positive? beta position, not the alpha. Okay? You're layering lots of stuff, right? And then I just threw a whole bunch of crap at you real suddenly. I expect you to get these things wrong, but we need to talk about why. Does that make sense? Okay? So you're saying you want to do the beta attack on this system. Okay, so let's adjust our answer. What we're saying is that we go through and do, I would draw it down at an angle, but it's kind of crowded. Okay? So we'd be putting something in at that position. Okay? And that would mean we just did a standard nucleophilic addition. Fair enough, we started with an acid-base reaction, right? Okay, I said, oh, nucleophilic addition elimination, and then I throw you an acid-base one. It is quite likely that I went through and did the same thing at you, okay, and said, review your stuff. Okay. But is there some other character going on with this structure? That piece is a really good leaving group. So while I do have that alpha beta unsaturated carbonyl kind of characteristics, it doesn't have the same withdrawing effects to make the beta position positive because the oxygen of our leaving group is doing resonance inwards. That minimizes some of that electron withdrawing effect, pretty much negating the beta position's reactivity. Okay. Which then means no beta position, I have to react at a carbonyl. But the problem is 2 carbonyls. Okay. So we said alpha beta, not a bad idea, but that donating effect of that oxygen's probably shutting that chemistry down. I now have to look at a direct addition at those carbonyls. Okay. Well, which carbonyl? Our nucleophile is going to react with what? And that was a vague enough question. I will let you get one dumb answer. That wasn't the dumb one, but that's good. Okay. Dumb one was, it reacts with the carbonyl. Yeah, okay. So we got that one out of the way. So it reacts with an electrophile. What electrophile should it react with? What electrophile should it react with? 2 focused on the question or the structure. The most positive is what it should react with. Now that I have that piece of information, I can go through and look at the structure. Which of those carbonyls is likely to be the most positive? So the red oxygen can donate equally both directions. Okay? So that's not a fair comparison because it's the same for both. Okay? The carbonyl is the same for both. Where's the difference? We're looking at the pi bond out here versus just a carbon. What can the pi bond do differently than that carbon? Resonance. What does that do to the positive charge? Makes it less positive. There's now electrons to stabilize it. What does that then mean? If it is less positive, the nucleophile should attack the right one. We form our tetrahedral intermediate, which is, we'll find some of us are entirely way too lazy about drawing, and there's 2 crowded in there already. We will reform the pi bond, and we'll kick out our leaving group. But I have a negative oxygen. That's not allowed. If it's not an allowed step, I can't move on beyond that. There's our answer. There's resonance to stabilize that negative oxygen, making it a valid maneuver. Now that I have established that it is okay to form, I can do the acid-base step to remove that hydrogen, and we'd end up with our final products, the NH2 and our carboxylic, I missed a carbon, sorry, our carboxylic acid. Kind of, sort of? What's the face?
Why the carbonyl was not eliminated? Like, I was expecting to see a double bond to nitrogen and the oxygen being completely gone.
It has to do with that structure in and of itself. What is special about that structure? That is an amide, it's an acid derivative. Right. So what you're thinking of is, can the nitrogen completely remove the carbonyl? In a nucleophilic addition, yes, absolutely. This isn't a nucleophilic addition. This was a nucleophilic addition followed by an elimination, which now staunched the reactivity. I now no longer have a carbonyl that a nitrogen can attack. I have an amide. That oxygen, that carbonyl carbon, is no longer as positive because the nitrogen can do resonance to prevent another nucleophilic attack. Okay. That bond is actually one of the strongest bonds, okay? Which is also arguably one of the reasons why we exist, is that bond. Because that bond is, it's an amide bond, it's an amide functional group, but biologists are notoriously afraid of chemistry, so can't call it by what it's actually called, and instead invented a new word. That new word, they called it, because it's so much easier to deal with, peptide. That is a peptide bond. That is the bond found in proteins, not in DNA. Not in DNA. No. I don't think it's in DNA. It might be in there, but it's not one of the main ones. Okay? 3. Okay. So finally, right, we got Br minus. Oh, and this time the carbonyls were symmetric, so we don't have to even argue. We're saying Br minus comes in, attacks, break the pi bond, reform, kick out our leaving group, and we'd have the product shown. Which is more stable as a negative? Bromide is larger than oxygen, so we're going back to our rules on establishing stability. Charge then size, bromide is larger than oxygen. Bromide's more stable as a negative than the oxygen, which then means there's no reaction. Dude, whoever wrote this quiz, man, just had to make everything stupidly tricky. No reaction. That one doesn't happen. Okay? And you know the reasons why. You're evaluating those patterns and trying to come up with explanations for why. Okay? One of the things that's unfortunate is we can see what needs to happen. That doesn't mean it does happen. Okay? Let's skip 4 for a moment because that's a bit of a beast. 5. Lithium aluminum hydride should look familiar. What did lithium aluminum hydride supply? Hydrides. What can those hydrides do? Direct attack to our carbonyls. Okay, so it can directly attack to form our carbonyl, or sorry, form our alcohol on the left. What kind of pseudo derivative have we formed here? What? What kind of pseudo derivative have we formed there? From practice exam 2 actually had this on it. You want a hint? What happens if we make that an OR? We now have an acetal. What's the issue with the acetal? lots of things. Acetals are inherently unstable and revert to their carbonyl structure. Okay. Which one is going to be more likely to be kicked off of that structure? The oxygen or the nitrogen? Or let's say it this way. Which one of those atoms would more likely leave the structure?
Oxygen?
Why?
Because it can hold their charge.
Why?
Because it's more electronegative.
Bingo. Oxygen's more electronegative. What happens? Our electrons can come back down, kick out the OH. What's the problem with that new structure? Ignore the fact that its charge is now fixed. You want a hint? Sure. What's the problem with that product?
Don't react again.
It'll react again. We have a polar pi bond. What reacts with lithium aluminum hydride? Polar pi bonds. The result is we'll end up reducing that fully down to the amine. Okay. The oxygen gets kicked out, not the nitrogen, because the oxygen is a better leaving group than the nitrogen. Okay. So far, so good? Okay. Looking at this, is this like, yeah, that's not too far off from what I already know, or is this like out of left field, what the hell's going on? I can go either way. I'm fine with it. Just want to know.
For me, it's just seeing, like, it's all chemistry, I know, but it's just.
So it's all familiar, but it's seeing all of these new steps and having to be able to track what's happening. Yeah. And that is what a lot of this section is just, it's chemistry that you know. You just now have to start thinking about the nuances of when and why you're allowed to do things. And again, all of those steps are things you know. Slow it down, look at your charge imbalances, evaluate stability, and just keep cranking through it. Okay? It'll take time and practice. And the reason why I'm delaying is we have to look at that last one, and to do that last one I just need to clear everything. So unfortunately, Sam, I appreciate your answer, but it's also pretty way wrong. Which I think you already knew. So, okay, so let's clear all that away, and let's bust out what I said as the hint. Okay, I said this was an acid-base step, followed by a substitution, officially in SN2, followed by our nucleophilic addition and elimination. Okay, acid-base. We're going to go this way. The hydrogen attached to the nitrogen is likely going to be the most acidic. Why?
Because it's the only one that is connected to a more electronegative.
Number one, it's the only one connected to an electronegative atom. Okay, why else would that nitrogen or that hydrogen be acidic?
Resonance.
We have resonance stabilization. Okay, through that structure is always fun to say. It's a phthalimide. Just in case you were curious. A bunch of H's in there. It's super exciting. So, the next part was an SN2. Why SN2 and not SN1? It doesn't form a carbocation, but that would mean looking at an intermediate. Okay, so I'd have to draw it and be like, well, there's no carbocation. Well, there isn't because you didn't draw one. Okay, what about our structure suggests that we should be doing SN2? Yeah, what is that? Charge, yeah, what charge? Negative, which would mean it is a strong nucleophile. Strong nucleophiles only run in SN2 conditions. Okay, so that's a big tip-off that we're going to do in SN2. What else should we be looking at? I can't get much bigger, otherwise it starts overlaying things.
Carbon.
Yes, it's carbon.
It's a partially.
Yep, it's partially positive. Why is that carbon?
Bromine's negative.
Yeah, yeah, but that would work for an SN1 too. What?
Gonna leave and take the electrons.
Yep, that still happens in an SN1. What about that carbon makes me say it's SN2? It's a primary carbon. Okay, that carbon is only connected to one other carbon. Primary substrates favor SN2. Right? Cool, we neutralize that negative. Now what do I do? I got the nucleophilic addition followed by the elimination. What's my nucleophile? OH minus. Where's my electrophile? What is an electrophile? Something partially positive or formally positive. There's no formal positive, so where's my electrophile? Carbonyl. So it can come in and attack, form our tetrahedral intermediate, come back down, kick out the nitrogen. Okay. We would form a carboxylic acid and an amine or an amide. Okay. We can protonate that amide with the acid of the carboxylic acid. That is an irreversible step, saying that that step happens. But wasn't there another carbonyl? Couldn't it have attacked that one? Should it also attack that one? Yep. And yes, we will look at this in a lot more detail later. Forming a carboxylic acid again, which could then protonate. And what do we end up with? Well, we'd end up here. Those being, well, that was kind of boring. What was the other piece? Why do we do all that? Your focus should be right here on this tiny little guy. What is special about that tiny little guy? Nothing special about it. Stupid. Yeah, the three-membered ring we started with, though. As a hint, this is not the chemistry, but this is part of it. This might jog some memories backwards. Want to start guessing some letters? There is an A. Ding. What? Boo.
R.
What?
R.
R? Did someone say O? Ding. No. E was already guessed. What game are we playing? What game are we playing? Hang what? Hoffman. When did we get a Hoffman elimination? I know, that was a long time ago, I know. Quaternary amines, right? Because we'd initially looked at nitrogen acting as a nucleophile, doing our substitution reactions, and we said nitrogen as a nucleophile was crap. Okay? The only reliable amine that we could get out of our substitutions was a quaternary amine, which we could only use for Hofmann. But what did I just make? A what? How do we count our primary, secondary, tertiary? How many carbons are connected to that nitrogen? 1. What did I just make? A primary amine. Okay. Back in that useful substitution chapter, we couldn't make anything other than quaternary amines. We can't make primary amines. Guess what we just made? A primary amine. By doing a crap ton of chemistry, admittedly, but we then made a primary amine. Kind of a neat reaction. Okay. And for whatever reason, when I see this reaction, I see wings. I think it's the phthalimide, kind of looks like wings. Okay. Which will make a little more sense later. Okay, so let's take a minute to break a little bit. Nomenclature, because we got to go back and review that. Remember, all of our rules, the big things that are coming in are our acids and our esters. Okay? For acids, the ending, our E, typical E ending, becomes an ic acid. Notice there's nothing to change it to, because acids are the highest priority in our naming system. Okay, so if there's some other functional group on there, it gets the one in parentheses from our other systems. Okay? Esters are acid derivatives. They would get the O8 ending. Okay, so we've talked about sodium benzoate before. Okay, that was the conjugate base of benzoic acid. So there's benzoic acid. If I remove the hydrogen, it becomes negatively charged. If I removed the hydrogen with sodium hydroxide, then this puts a sodium there, and I have now sodium benzoate, because that piece is my ester piece. Okay? If instead of it being sodium, it was a single carbon, then it becomes methyl benzoate. So all we're doing is naming the substituent that comes on the oxygen, and then the rest gets the O8 ending. Kind of, sort of. Okay? So again, you need to know these, study them, review them, make sure you've got them nailed down. Okay? And as much as I will say it is stupid to lose points on nomenclature, again, that's where I accepted point loss when I took OCHEM. Okay? They're just knowing rules. If you can know rules, then nomenclature should be right up your alley. Just learn the rules and you should be fine. Okay? Practice. Yay! So, I will give you till 2:05, which is like 4 minutes. Minute per structure. We have 2 carbons, so we're looking at an ethyl, or an F. Okay. We said we have a carboxylic acid, which then makes it ic acid. Okay, but that's also substituting the E, so we lose the E. Well, where's the E? I haven't put in the E yet, because the section that's missing is our hybridization of our carbons. Okay, ane, ene, or ine. So if we look at just the carbons in the backbone, how are they all connected? Well, sigma bonds. So we're looking at ane. This needs to be ethanic. God, ethanic? We can do better than that. Ethanoic acid. And we'll drop that O in there just to make it sound cooler. Okay, or at least that's my rule for it. The bottom one, I've got 2 numbering system here. Both of them are 1, 2. So minimally, we're looking at an F and an F. But now the question becomes, which F is F? Okay. When we are naming, this F is our highest priority, because it includes the sp2 carbon, our higher priority. So the other one becomes a substituent. That will then become our ethyl. Substituents always get included in front of the name, so it's going to be an ethyl, and now we have to name the rest of that. Well, it's an F. Again, single bonds, our hybridization, and our ester name was OAte. We get ethyl ethanoate. That wasn't the easiest one to say, Cass. Lower right-hand corner, we've got 4 carbons, so we're looking at a bute. Okay. All sigma bonds, so we'll go butane. Our functional group, well, it isn't an acid, it's the conjugate base, so it's effectively an ester with potassium as its substituent. So I can go with potassium. Did I spell that right? I don't know. Butanoate. Kind of makes sense? Okay. The top one, well, we've got 1, 2, 3, 4, 5, 6 carbons. That's long. Oop, but that didn't include the carboxylic acid, so 5 carbons. No, because we have to go through the double bond. We're only looking at 4 carbons in our name with a propyl substituent and an aldehyde substituent and officially an alkene. Sweet, this name is awesome. Okay, so 4 carbons in our main chain, so we're looking again at a butan, what? Son of a... Gah, I hate these names. Butene, you're right, we have to specify the location of the double bond. Where is it? Position 2. But2ene. Four ic acid, is that where you're going with that? It's going to be 1. Remember, our carboxylic acid is the highest priority functional. We'll come back to that guy in a second. So we could say but2ene 1, probably have to do oic acid. Because the acid is by definition starting at our beginning of our structure, we can ditch the 1 and we can just call it enoic acid. Okay. Lose the space there, but I don't want to erase and do it again. Okay. The other part that we have to stress about is that aldehyde. So there was a suggestion that I got to do a 4 for the aldehyde, but then that would be Al. Al is the ending of this. The oic acid is higher priority. The Al can't be the ending. How do I specify my aldehyde? It's the oxo at 4. 4-oxo-but2-ene oic acid. And son of a, I'm still wrong because I forgot the stupid propyl. And to make it even worse, O comes before P. 4-oxo 2-propyl but2-ene oic acid. And we officially have a cis-trans system that we would have to worry about here. Yeah, I was kind of trying to be obnoxious with this one. Our higher priority functional groups are on the same side of that. We should throw out in the front. This is cis. Cis is on the same side. So 2Z 4-oxo 2-propyl but2-ene oic acid. Yay, nomenclature. Okay. So after all of that, let's go back and look at that starting structure. Upper left-hand corner. We called that ethanoic acid. Does anybody call it something else?
Acetic acid.
Why'd you call it acetic acid?
It's a common name.
Because it is acetic acid. Okay. Why is it called acetic acid and not ethanoic acid? It's a common name. Okay. It just happens like water. Why do we call water water and not dihydrogen oxide? Okay. So the nomenclature system behind it is ethanoic acid. Some acids have common names associated with them. Acetic acid is one of them. Okay. You should be somewhat familiar with the common name for the acetic acid, because we'll encounter this functional group a lot. That functional group is known as a, or an. It's not an aldehyde because there's a CH3 there. and I haven't specified what's coming out of it. As a hint, it begins with A.
C. It's a thing.
It's an acetyl. Okay, so I don't think we've done acetylations yet. Yeah, so acetylations we'll eventually see. In fact, this is probably the section that we're going to see them. Okay, kind of makes sense. So keep that in the back of your mind. Maybe go back and review nomenclature in the earlier sections of our textbook. Okay, remember our textbook said nomenclature sucks, so they got rid of it all in the first semester, and I completely agree with them. Okay, so there is not any full nomenclature review for this section or this semester. Go back and look at those nomenclature review chapters for that practice. Does that make sense? Okay. And with that, I don't even want to look. Oh, well, shoot. We do kind of have to look at these. Some extra kind of random things coming out of this. I referred to the bond there as an amide bond because that is an amide bond. Okay. Also a peptide bond. How would I name that piece? Because that's not part of the main chain. Okay. It is a methyl, but I can't really call it methyl acetamide because that methyl group is attached to a weird location. It'll get referred to as N-methyl. Yes, there's an H in there. It's silent. Okay. How about the next one? Where would I specify the location of those methyls? There's two of them, right? So it has to become dimethyl. Why do I have to say NN? I have to specify the location for every single one. Okay, so that does go in as NN dimethyl. Okay. A carboxylic acid sort of can react with itself to form this new functional group. That new functional group is known as an anhydride. Why is it an anhydride? What did I lose between these two molecules to make the anhydride? I lost water. Okay, that's where the anhydride term is coming from. Okay, after that, you're not responsible for naming those that I can remember. They're just kind of the basic nomenclature pieces. And with that, I think we can, I won't continue on. I promise. I'm stopping. Okay, but we'll pick up on Wednesday with spectroscopy and then get moving back into the chemistry side of it.